Hi everyone! Today let's talk about Chapter 4, Probability Distributions, Section 4.1, Random Variables. We will start this lesson with an example. Let's look at example 1. Suppose you are performing a random experiment of flipping a coin 4 times. First questions. Could you list the sample space? How many possible outcomes are there? Alright, so we flip the coin 4 times, so we can write it as S1, S2, S3, S4, where the SI, they're either head or tail. Okay, and I goes from 1 to 4. Okay, so this is one way we can write the sample space. We describe it. And what is the size of S? Well, you can see each flip, we can have 2 outcomes, either head or tail, right? And we have 4 flips. So that's why this is 2 to the 4th, and it is 16. And then if we want to list all the outcomes in the sample space, it's better to draw a tree diagram. So let's say the first flip, it could be head or tail, right? And then the second flip, it could be head or tail, head or tail. And then the third flip, it could be head or tail, head or tail, head or tail, head or tail. And then the fourth one can also be head or tail, head or tail, head or tail, head or tail. Oh, almost ran out of space. Head, tail, head, tail, head, tail, head, tail. Okay, everyone? So now let's write it down. Okay, so they are, first one, head. And then head, tail. And then head, tail, head, tail, tail. And then we have head, tail, head, tail, tail. Is it head? Oh, head, tail, head, tail, head. Oops, sorry. Head, tail, tail. And head, tail, tail. Okay, the next one, tail, head. You realize these are the same. Just change the first 2. So tail, head, tail, tail, head, tail, head, tail, head, tail. Last one, tail, head, tail, head, tail, head, tail. Okay, so these are the 16 outcomes. Okay, question 2. If we make up a variable x and let x be the number of times the coins come up heads in 4 tosses, what are the possible values of x? Well, x is number of heads. Number of heads, it could be 0, 1 head, 2 head, 3 head, or 4 heads. How about 5? No, because we only have 4 flips. You cannot get 5 heads, right? Okay, question 3. What is the probability of each value listed for x in part 2? Let's organize in a table format. Okay, so 0, 1, 2, 3, 4. Probability x equal to 0, well, it means we have no head. So which means all of them are tail. And there's only one outcome, the tail. So because here we have 16 outcomes in the sample space, and they are equally likely. So that's why here 1 outcome over 16 is the probability. How about 1 head? Well, how do I figure out 1 hat? Well, here we have 4 flips, 1 hat, which means we have 4 boxes. We want to pick 1 boxes to fill with the hat, and then the other box is just tail. So that's why, oops, sorry, we have 4 choose 1. Okay, so 4 boxes, we choose 1. What is that? 4 choose 1 is 4. So that's why 4 choose 1 over 16, 4 over 16, which is 1 over 4. Okay, 2 hat is like we have 4 boxes, we pick. Oh, it's so sensitive. My hand sometimes touch the right lower corner. Okay, so sensitive. Okay, 4 boxes, we choose 2 to fill with the hat. 4 choose 2, 4, 3 over 2. We cancel. 2 times 3 is 6. Okay? So that's why this is 4 choose 2 over 16, which is 6 over 16. That is 3 over 8. And then 3 hats. So also we want to choose 3 of them to fill with the hats. So 4 choose 3. Okay, if you can remember, when we learned combinations, we have n choose n equals n choose 0 is 1. N choose n minus 1 equals n choose 1 equals n. Then n in general, n choose r equals n choose n minus r. So in this case, 4 choose 3 is the same as 4 choose 1, which is 4. So that's why here 4 choose 3 over 16 is the same as 4 choose 1 over 16. So we'll get 1 over 4. And then 4 hats. So just hat. So that's why this is like 4 choose 4, which is 1. Or 1 over 16. Okay, and what is the sum of p of x for all the values of x? Let's see. 1 over 16 plus, let me write down 4 over 16 instead of 1 over 4, because we want to have the common denominator so we can add them. And then 6 over 16, and then this is also 4 over 16, and this is 1 over 16. What is that? The denominator is 16, and the numerator, this is 10, and then this is 5, this is 1, so 16. Okay, so do you see the sum is 1? And it makes sense because we add up all the possibilities. That should be 1, because the probability of the sample space is 1. Probability of the empty set is 0. Okay? So what we just did is we just construct a discrete probability distributions. In part 2, we made up a variable x to represent the number of times the coins come up heads in 4 tosses. That variable is called a random variable. Okay, so a random variable represents a numerical values associated with each outcome of a probability experiment. It is a function from the sample space to the real numbers. There are 2 types of random variables, discrete and continuous. So the random variable is really like a function. Okay, so if you can remember, if we say y, let me use a different color. So how about let's use blue. So y equals f of x, and then we say x is the independent variable, y is the dependent variable, and f is the function, right? So here the x is actually a function. A function maps from S to R. Okay, so that's why here we get x 1, 2, 3, 4. So those are numbers in the real numbers, right? They're the real numbers. Okay, so x is like it maps, so 0 0 corresponds to like the tau 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 tau. It maps the tau 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 to 0. Okay, and then the 1, etc. So it maps the the other outcomes, like a head tail head head, or tail head head head, or head head tail head head tail to 1. Okay. All right. So you can write it down. Tail head head head. Oh, sorry. One head. So head tail tail tail. Tail head tail tail. Tail tail head tail, and tail 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 head. So map all these to 1 because the number of heads in these outcomes is 1. Okay, etc. So x is a random variable, and it is actually a function from the sample space to the real numbers. Okay, so two types of random variables: discrete and continuous. A discrete random variable has a finite or countable number of possible outcomes that can be listed. So countable, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is countable. Okay. A continuous random variable has uncountable number of possible outcomes represented by an interval on the real number line. So on the real number line, for example, the interval is 0 to 1. There are infinitely many numbers there, and actually those numbers are uncountable. Okay. All right. So our previous example, you can see because the x maps the sample space into these 5 numbers, 0, 1, 2, 3, 4. So that's why this is finite number. So x is, so in this case, x is a discrete random variable. Okay. All right. Example 2. Roll a pair of fair dice, blue and red, and the outcome is, okay, so blue and red, so that's why it's like we have an order pair I and J, and the die has 6 faces, so that's why we have 1, 2, 3, 4, 5, 6. Okay, and let's say the first one is the blue die, and then the second one is the red die. Okay, and what's the size of S? So the first blue die we have 6 choice. The red die we also have 6 choice. That's why we have 36 outcomes, right? And because all outcomes are equally likely, so each outcome has probability of 1 over 36. Okay, now let me give you some examples of random variables. We can let x1 of ij be I. So what does this mean? This means we just want the number on the blue die. Okay. Let x2 of ij to be j. So this is just the number on the red die. And let's define f of ij to be the sum I plus j. Okay, so these are random variables corresponding to the number on the blue die and the number on the red die, and then the sum of those two numbers. 8. Okay, and then let me ask you, what is the probability that the sum equals 8? Well, this is the same as saying We're looking for the probability when f equals 8. Okay, what is this? Because all outcomes are equally likely, well, this is just the size, the number of elements in the events f equals 8 over the total number of outcomes in the sample space, which is 36. Okay, so how many outcomes are there? So, okay, this guy, by the way, this notation, this is the shorthand for P of I, J, such that I plus J equals 8. Okay, and that is, what are the elements? Okay, can the first one be 1? Okay, the second one is at most 6, but when add them together, this is 7, so this is impossible. So the first coordinate must be at least 2. So 2, then we have 6. 3 plus 5 is 8, so 3, 5. 4 plus 4 is 8. 5 plus 3 is 8. 6 plus 2 is 8. And that's it. How many outcomes are there? 5. So that's why we get 5 over 36. Okay, and here each outcomes is equally likely. Okay, so we mark. So P of x1 equals 2, x2 equals 5. This is the same as P of x1 equals 2 and x2 equals 5. So I just want to show you more different ways of writing the same thing. And this is the same as saying P of, let's see, x2 equals, x1 equals 2, intersect, x2 equals 5. Okay? And it's also equal to P of x ij such that x1 of ij equals 2 and x2 ij equals 5. And this is the same as P of the outcome 2, 5. And because there's only one outcome, we get 1 over 36. So all of this represent the same thing. Okay? Alright, how about x1 equals 2 or x2 equals 5? Well, if instead of and, now we have or, this means this is the x1 equals to 2 union the event x2 equals 5. Okay, and this is the same as P of ij such that x1 of ij equals to 2 or x2 of ij equals 5. And what are these? Well, okay, remember this is like or, so that's why we can use the general addition rule. So this is P of x1 equals to 2 plus P of x2 equals 5 minus P of x2 equals to 2 and x2 equals 5. Well, how many outcomes x1 is 2? Okay, 6 outcomes, right? So because the second die could be any number. And then what is P of x2 equals 5? Also 6, because the first die could be any number. And then there's only one outcome, the 2, 5, right? So, and don't forget we have the total is 36. So 12 minus 1 is 11 over 36. So far, so good, everyone. Okay, third. A random variable is a function, not a variable. So a random variable is a function. So x from the sample space to the real numbers. And it is not a variable. Okay, even though it calls it random variable, but it is a function. It's not a variable. Okay, so and IE for a W, an outcome in the sample space. Okay, this is an outcome. We get X on W. This is a number in the real number set. So this is a real number. Okay. Fourth, the set XW where W in S, it is the range of X. If the range is countable include finite, then we will say X is a discrete random variable. So for now, it makes sense to just look at the range of X. Okay, so we don't really care about the domain S, the sample space, might not be countable, but as long as the range of the random variable is countable, then X is a discrete random variable. So we will go over an example to talk about this. All right, example 3. Take a number uniformly at random from the interval 0, 1. Then the sample space is the interval 0, 1. And how many points in the interval? There are infinitely many, actually uncountably many. Okay, and then what is the probability of A to B? Well, this is actually B minus A. And why? Because for events here, probability of A should be the length of the interval over the length of the sample space. And so that's why if we have an interval, this guy should be the length of the interval over the length of the sample space 0, 1. The 0, 1 is just 1 minus 0. And then the length of AB is B minus A. But because the denominator is 1, so that's why we have B minus A. Okay? So this is the probability of an interval, a subinterval in 0, 1. But the probability of a single point is actually 0 for all the x in 0, 1. Okay? And it kind of makes sense because if the probability of a single point is not 0, and there are infinitely many points in this interval, so when we add infinitely many positive numbers, the answer is will exceed 1, right? Actually, uncountably many points there. Okay, so it will be a trouble. So the probability of a single point is 0. Okay, now let's let y w equals 2w for any w in the interval 0, 1. Then for any a in the 0, 2, what is probability of y less than equal to a? Okay, so this is the questions. Okay, so we define a random variable y of w equals 2w for any w in the interval 0 to 1. And for any a in the interval 0 to 2, what is the probability of y less than equal to a? Alright, so let's see. Probability of y less than equal to a. And because y equals 2w, so this is the same as 2w less than equal to a, So this is the same as w less than or equal to a over 2, because we can divide it both sides by 2, and 2 is a positive number. It won't change the inequality. Okay, and w, remember w is in 0, 1. So this is the same as w is in 0 to a over 2. Okay, and what is the probability of this guy? Well, just a over 2 minus the left endpoint 0. So just a over 2. So the probability is a over 2. And here you can see the range of w is an interval, so is uncountable. Okay, so y is a continuous random variable. Okay, and because the range of y is uncountable. Okay, and in chapter 4, the remaining chapter 4, we will talk about more discrete distribution. And in chapter 5, we will talk about continuous distribution. Okay, let's continue. Each value of a discrete random variable can be assigned a probability. By listing each value of the random variable with its corresponding probability, we are forming a probability distribution. In example 1, our random variable x is the number of hats, so we have a discrete probability distribution. So in example 1, you see this table. This table is a probability distribution. So we have the x values and we have the probability at that point, okay, at that value. All right. Definition: the probability mass function PMF of a discrete random variable x is the function p from the range of x to the interval 0, 1, such that the probability of x is the probability x equals to x. So here we have 2x. So this x is a random variable. This x is a fixed value. Okay, so this small x is a value from the range of the random variable. So it's like, well, p of 2 is probability when x equals to 2, etc. Okay, and we can also denote this probability mass function of this random variable x to be p sub x. Okay, so capital X, the random variable, small x is a value of the range. So when you write your answer in your homework or exams, please make sure I can tell which one is the big X, which one is the small x. Okay? Alright, so let's continue. Alright, couple remarks. Okay, so probability of x in a set B, events B. This is the sum of x in B of px equals to small x. Okay, so the x's are the outcomes in B. So, and also we need x in the range of the random variable. Okay, so this is the same as x in B, p of x. And this is a countable sum. Okay, so probability mass function is only for discrete random variable. So we assume x is discrete. Random variable. Okay, so then this is a countable sum. For random variable x, for discrete random variable, the range is countable or finite. Okay. And we also know all the px is between 0 and 1. Okay. And so this number is also between 0 and 1 because when we add up all the probabilities of all the outcomes, that is the sample space. The sample space has probability 1. Okay. So example, Px in R. Oh, this means sum x in the range of x of Px equals x. And this is 1 because the probability of the entire sample space equals 1. Okay? And notice that this adding something only works for discrete countable sum. Okay? For continuous random variable, we will have the probability density function, which is called PDF. So for discrete random variable, we have PMF, probability mass function. For continuous random variable, we have PDF, probability density functions. And we will integrate it. So we will integrate it, so not sum. For discrete random variable, we sum, we add the probabilities. But for continuous random variable, we integrate the PDF. Okay, we don't add them. Alright, so we'll talk about this more in chapter 5. Alright, so now let's look at an example for throw darts. Have you ever thrown some darts? So let's make the games more simple. So let's just consider this picture. Okay, so the radii are 1 for this smallest circle. Okay, so this radius 1, 3, 6, and 9. And the values are 10, 5, 2, 1 points. So when you hit the center, you get 10 points. And if you hit this red circle, you get 5 points. And then you get 2 points and 1 point, etc. So W is a point on the board. Okay, this board is a disk of radius 9. If W is chosen uniformly at random, find the PMF of X. Okay, so let's see. Let's compute from the middle. So what is P of 10? So P of 10 equals P of X equals 10. Alright, and because all the points are equally likely, so we can use the area of the small circle over the area of the board. Okay, what is the area of the smallest circle? It has radius 1, so pi r squared, pi times 1 squared. And the entire board has radius 9, so pi times 9 squared. So pi cancel, we get 1 over 81. Okay, so that is P of 10. And then next, P of 5. Okay, so that's the same as P of X equals 5. Okay, what is this region? Well, this region is actually the annulus, right? You cannot be in the inside circle, because if you're in the inside circle, you get 10 points instead of 5 points. So 5 points is like the annulus. So it's the area of these annulus over the the entire board, right? The area of the entire board. So this annulus is pi of the outer circle with radius 3, so pi times 3 squared, minus pi times 1 squared, over the board pi times 9 squared. So pi's are cancelled, and 3 squared is 9, 9 minus 1, 8, 8 over 81. Alright, and then how about p of 2? Well, that's p of x equals 2. So you can also like pause the video and then continue to write down p of 2 and p of 1. Have you finished? So this is pi, the radius is 6, so 6 squared minus pi 3 squared over pi 9 squared, so which is this annulus, right? And then 6 squared 36, 3 squared 9 over 81, we get 27 over 81. Well, that is the same as 1/3. And then finally, p of 1 is p of x equals 1. That's pi of 9 squared minus pi 6 squared over pi times 9 squared. So 81 minus 36 over 81. Which is 45 over 81. Okay, we can divide it by 9, so 5 over 9 is the answer. Okay, so far so good. Now, so we have the random variable, the range are 10, 5 to 1, and now we get a PMF for x. All right. Okay, so let's see. If I ask you more questions, let's see. Okay, if I ask you questions, what is the probability x in the interval 1.6, 6? Well, look at the range, 1, 2, 5, 10. Which number is between 1.7 and 6? Well, we just get 2 and 5, right? So this is p of x is 2 plus p of x is 5. So x is 2, we get 1/3. X is 5, we get a over 81. Alright, so, is that 1/3? Maybe we should take 27 over 81. Then we have the common denominator. Then we get 35 over 81. Okay? And also, notice that x is a discrete random variable, but our sample space is uncountable. Okay, so when we throw the dots, do you really care where the location of the dot is? You just care about the points, right? Which circle it lies in. So for example, these 5 dots, you get 2 points. Okay, so you don't really need to know the exact location of the dots. You just need to know, okay, you get 2 points there. So that's why in this example, because the range of x are the numbers 10, 5 to 1, this is a finite number. So x is a discrete random variable, okay, even though the sample space is uncountable. So that's why we should look at the range of the random variable to tell whether it is a discrete random variable or a continuous random variable. Okay, so here we can also draw a table to indicate this. So to indicate this PMF, okay. So this is the PMF, and we have the x values. Okay, the PMF so x could be 1, 2, 5, 10, and for 1, the PMF P of x equals 5 over 9. Okay, when x is 2, P of 2 is 1/3. When x is 5, P of 5 is 8 over 81. And when x is 10, we get P of x is 1 over 81. So we can write it down in a table like this. We can also draw it in a graph. Okay, so let's draw the graph. Okay, so here I'm gonna draw 2 different graphs to show you. The first graph I draw is a probability histogram. Oops, sorry. So a probability histogram, you have x-axis, and this is P of x. And then we have 1, 2, 5, 10. It might not be in the same scale because we just need 4 numbers there. Okay, and then when x is 1, we get 5 over 9. Okay, let's say this is 1. 5 over 9 is right here. Okay? And when x equals 2, we get 1/3. So 1/3 is like here. P of 5, 8 over 81. So like that. P of 10, 1 over 81, like that. So this is a probability histogram. Okay? And we can also draw it as probability bar chart. So probability bar chart. Okay, so then we put x and P of x. It's very similar. So we also have 1, 2, 5, 10. And then so for bar charts, you just this is 1, and we need 5 over 9 right here. So bar chart is just you connect these, and this is 1/3 right here. You connect this. This is 8 over 81. Connect this. Finally, 1 over 81. You connect this. So this is the probability bar chart. Okay. And so now we just talk about PMF. Okay. Next, let's talk about cumulative distribution function, CDF, of a random variable. So PMF is only defined for discrete random variable, and PDF is only defined for continuous random variable. The CDF, cumulative distribution function, is defined for discrete random variable and continuous random variable. Okay? So f of x equals the probability of x less than equal to x. So cumulative. So not only x, also the previous values, we also want to add those probabilities. Okay? So f is a function from the real numbers to the interval 0, 1. Okay, continue with the last example. Find the CDF for x. Okay, so we can continue with the table. So our table, we have x, we have the PMF, P of x. Now we have the CDF, P of x, f of x, sorry, capital F of x. We use it to denote CDF. Okay, 1, 2, 5, 10. So this is 5 over 9. This is 1/3. This is 8 over 81. This is 1 over 81. Okay, CDF is x less than equal to that value. So less than equal to that value, okay, it would just be 5 over 9. And less than equal to 2, well, you should add all these together. So you get 5 over 9 plus 1/3. 1/3 is like 3/9. 5 plus 3 is 8. So 8/9. Okay, how about this guy? Well, this guy means you should add all the possibilities before and equal to this point. This 5. So you add those 3 numbers, but to make it easier, because this number is already all the probabilities before that, so you actually just add those 2 numbers together to get this. Okay, so you get a/9 plus a/81, and the answer is 80/81. Okay, and then finally, what happened? This guy add this guy, you get 1. Okay, and that's what happened because you see all the probability are right here for these values. So where the x you pick is greater than 10, then the probability is 1. Okay. So let's draw pictures of the CDF. Okay, so let's see. F of x, oh, we can write this down as, so it's 0 when x is between -infinity and 1. At 1, okay, so when x is 1 to 2, and not include the 2, we get 5/9. When x is between 2 to 5, not include the 5, we get 8/9. And when x is between 5 to 10, not include 10, we get 80/81. And if x is greater or equal to 10, we get 1. Okay, so the picture, so this is x, f of x is right here. And what is that? Okay, so we start with the numbers 1, 2, 5, 10. Okay, it is 0 when x is less than or equal. So because we don't include the endpoints, we put or maybe let me use a different color, then you can see the difference. Okay, so we don't include the endpoints, and we get 0 when it's before. And then at 2, from 1 to 2, we get 5/9. So include this point and exclude this point. And then we get 8/9. And then we get 80/81. So, and after, when x is greater or equal to 10, we just get 1. So, okay. So this is the graph of CDF. Let's figure out some properties of it. What can you say about this picture? Okay, so, oops. Oops. So, alright. I think I need to save my Word documents. Okay, so, what are the properties of CDF? First, what do you say? Can you see the values are in like a bigger? Okay, and we cannot say increasing because sometimes it could stay the same. The correct word for this is non-decreasing. So F is non-decreasing. So it means it could increase at some points and stay constant, and increase and stay constant, like this. Okay? And you can see F is positive, right? And F is also smaller or equal to 1. And furthermore, when the x goes to -infinity, we will get the limit is 0. Okay? And on the other side, if x goes to infinity, the limit is what? 1. Right? And can you see here the right side limits equals to the function value? Do you see this solid circle? Okay, so this means f is right continuous. If you took calculus 1, I hope you did. Okay, f is continuous. Okay, so let me write it down here. Okay, so f of x is continuous at x equals to a if limits x goes to a, f of x equals f of a. Okay, so this is continuous, so which means there's no hole there. Okay, and f is right continuous means the right side limit equals to the function value. So which means you have something like this. So this is right continuous. When you approach the point on the right side, it matches with the function value. Okay, so this is right continuous. So our CDF is actually right continuous. Alright. So in general, if I give you a PMF, you can find the CDF. If I give you a CDF, then you can find a PMF. Okay? If you want more example, we can probably do more example here. So here I just create two charts table. Okay, so let's fill it out. The first table, we know the PDF values and we want to find the CDF values. Okay, so the first one, because P of minus 1 is 0.1, so the CDF f of 0.1 will be 0.1. Okay, and here, next one, so this is, remember, this is the probability x less than or equal to the small x. So probability x less than or equal to -1 will be 0.1. And then here, when x is less than or equal to 2, we just add these two together, so we get 0.4. And then to get this number, we just add these two together, we get 0.8. And then to get this number, we add those two numbers together, we get 1. So this is the CDF. Okay? And then on the other hand, how to figure out PMF? Sorry, this is PMF. Okay, the first one stay the same, right? And then, how do we get this number? We use this guy minus this guy, so the difference. So 0.55 minus 0.2 is 0.35. And then we use this guy minus this guy, the difference is 0.2. Right? And then we use this guy minus this guy, the difference is 0.25. So this is how we get the PMF from the CDF. Alright, so if you have questions, feel free to ask me. Bye!